Hello YouTube, it's been a minute. Today we're going to be talking about hills. It's going to be a pretty quick one. We're going to save the harder hill problems for later. Just a quick example of like what the strategy is, how you're supposed to do it, and then set you loose. So, hills. Pretty much we're just going to talk about how to model the motion of an object on a hill. We're rotating our reference frame. This makes our system of equations much easier than it otherwise would be. In particular by eliminating the acceleration in one of the directions. So instead of having there be acceleration in both the x and y direction, we make it so it's only accelerating in one of those two. So let's say I've got an object sliding down a hill, as shown, with a force of 20 newtons worth of tension acting on it on the string that's shown right along here. Find the acceleration of that object and ignore friction. That last part's going to be pretty important for getting the system easier, and we just haven't learned about friction yet. So, all right, let's get our info down. So in particular, we know that we've got our hill, and we've got a box on the hill, which is 3 kilos. We've got this force of tension, which is 20 newtons, going off at an angle of 30 degrees above the hill. The hill is at an angle of 37 degrees with level ground, and the velocity is not going to matter because we're ignoring the friction. All right, so pretty much if we go about this one the way that we would have previously, we'll get our dot for a free body diagram, and we'll get our force of tension, which is 20 newtons. Do a dotted line for my hill. 30 degrees above that, which is 37 degrees above the horizontal. We'll have gravity going down, and we'll have normal force going perpendicular to the hill. Now, if I were to break this up into components, there's going to be some problems. In particular, my x and y components for these two are going to exist. They'll be fine, right? I can use sine and cosine. I can figure out what this angle is. If this is 37, then this is 37, then this is 90 minus 37, which lets us get those angles. The geometry is a pain, but you can do it. And when we do that all out, we'll wind up with an x equation where our net force in the x direction will be equal to the normal force x component negative plus the force of tension's x component, and that'll need to be equal to mass times acceleration in the x direction, because this block is accelerating diagonally. So there's going to be a component to the acceleration in the x direction and a component to the acceleration in the y direction. If we look at the y direction, we'll wind up with something like this, where we've got negative mg plus our normal force in the y direction plus our force of tension in the y direction. Both of these are going to be a little bit of a nightmare from a geometry perspective to figure out, but they'll exist, you can find them, and it'll work. And there'll also be that acceleration in the y direction, which should wind up being negative, depending on how strong tension is, actually. The problem with all of this is that if we are trying to find the acceleration, once we represent these as a combination of sine and cosine of the hill angle, because it's going to be along the hill, they will only be one variable. Our only other variable here is normal force, and so we can solve it out. We have a system with two equations, two variables. That's going to be miserable. And again, the geometry is going to be miserable. And you can do it, but it's a pain. This problem gets a lot easier, though, if we take the sheet and we turn it like this. Because if we take the sheet and we turn it like this acceleration right here, just let me get that in a different color. Admittedly, this is not going to be a particularly clear color, but it will at least be a different one. Or the pen's dead. Let's try a more other one. Great. Our acceleration will not have an only component if our acceleration is pointed in our new only x direction. The only thing that's kind of weird about this picture is that gravity doesn't go straight down. Now, it still goes straight down, right? We're just rotating our head. But from this reference frame, the center of the Earth just isn't straight down from the way that we're facing, which is fine. And this acceleration, instead of thinking about it as the x and the y component, although in our new rotated reference frame it would be the x and the y component, the way we'll be thinking about it is parallel to the way the hill goes and perpendicular to the way the hill goes. And if we do that, everything suddenly gets a lot easier. So I'm actually going to redraw my reference frame for the shortcut way of doing this problem. So we've got our dots still, we've got our hill, and we've got level ground, and that'll become relevant in a second. Now gravity is going to be perpendicular to that level ground, so this is mg. This angle right here is 37 degrees, which will matter for some geometry in a bit. Perpendicular to that hill, we've got the normal force, and in addition, we've got our tension, which is going off with 20 newtons at an angle of 30 degrees above the hill. So this is 37 degrees, which means that this is 57 degrees, or sorry, 53 degrees, which means that this is 37 degrees. And that angle matters because this is my new component for gravity, and this is my second component for gravity. And that's a little weird because we're not really used to breaking up gravity into components for the other problems because it was just only going in the y direction. That is a little bit of a price you have to pay, and it is kind of annoying to remember that the hill angle is not the angle that's adjacent to the x component in this new rotated reference frame. It's the angle that's adjacent to the y component. So the perpendicular component of gravity is going to be mg times the cosine of theta. And the parallel component for gravity is going to be mg times the sine of theta. On the flip side over here, for our force of tension, we'll have Ft perpendicular being Ft sine theta, and the parallel component being Ft cosine theta. 30 though, in this specific case. And our normal force is just perpendicular. That one actually is nice and easy. So when we set up our equations, we're going to have a perpendicular equation and a parallel equation instead of an x and a y equation. And you could just write this as x and y as well, and no one would really bat an eye at it. Oops, to the extent where I just accidentally did the wrong one. So in the x direction, we've got our force of tension pulling it forward, or to the right. And we've got our force of gravity pulling it down the hill. And I should call this like theta 1, theta 2. And that will be equal to mass times our acceleration. Specifically our acceleration that's along the hill or parallel to the hill. I ran out of room on the sheet of paper, which is why that is a very wimpy parallel symbol. In our perpendicular direction, the entire reason we did this is that we've got our normal force going up, we've got our force of tension going up, and we've got our gravity going down, but only the perpendicular component of it. And so that's going to need to equal 0 because it's not accelerating into nor out of the hill. And what's nice about this is actually just a one-step problem to solve as long as we've got the right angles. We're trying to find the acceleration, so just divide by mass. Great, we found the acceleration. Acceleration along the hill is going to equal Ft times the cosine of theta minus mg times the sine of the hill angle divided by the mass of the object. So in this case, plugging in our numbers, we've got 20 times the sine of 30 minus 3 times 10, so 30 times the sine of 37 divided by 3. And you can put that into the calculator and get an answer. I'm feeling like I don't actually know where a calculator is in my house right now. So we'll leave that for another day. I do think it's worthwhile to sort of summarize everything that we did there. But that's pretty much how you do these problems. So in particular, once you rotate your reference frame, think of it as parallel to the hill, as in going up or down the hill, and perpendicular to the hill, as in smushing into the hill or pulling off the hill, instead of X and Y. And when you do that, gravity will be diagonal. One of the few things all year that honestly I just memorized because the geometry is weird for it. The component that goes along the hill and down the hill for gravity is going to be mg sine theta, where theta is the hill angle. The component going perpendicular to it is going to be mg cosine theta. Your perpendicular acceleration will be 0 unless you're either tunneling into the hill or lifting off the hill, in which case it will not be 0. And that's pretty much how you approach these. So, short one. I'll try to get a video posted that goes over how to do 2 harder ones next. So, goodbye, YouTube.